Hello and welcome. This is the CHMB42 video presentation on substituent effect on electrophilic aromatic substitution or EAS reactions. As noted here, it's an animation project by myself, Vanessa, and Sekar Wangi. And throughout these slides, we'll see how substituent on a benzene ring will influence both the speed of EAS reactions and where new groups will attach to the ring. Let's go to the next slide. On this slide, we see a generalized electrophilic aromatic substitution, known simply as EAS. You can see here there's an electrophile which is positively charged, and it reacts with a benzene ring, which will be here in this case react as an electrophile, and it will get attached to the benzene ring by EAS reaction. An example of EAS reaction here is nitration reaction, where you react the benzene ring with concentrated sulfuric acid and concentrated nitric acid. It will react and become a nitrobenzene, and this nitrobenzene can be further reduced using tin and hydrochloric acid to become aniline, which is very helpful in our everyday life and is widely used as dyes.
So, what are substituents exactly? Substituents are atoms or groups of atoms that are attached to the benzene ring. For example, in this slide, we have G, which is a placeholder for substituents, and then beside it, it's an ortho position, and then the carbon after that is a meta position, and the carbon that is exactly across the substituent is called the para position. So substituents have many effects on the EAS reaction. For example, it can change the reactivity of the benzene ring, which will impact the rate of reaction. It will also change the position of where substituent will occur. For example, whether it will be ortho-para position or meta position.
There are two effects of substituents. The first one is activating group or electron donating group. This group will increase the electron density of the ring, making it more reactive towards EAS. It will direct electrophiles to ortho and para position because of resonance and inductive effects that stabilize the intermediate carbocation. An example of activating group is hydroxy group, amino group, and methyl group. The second effect is the activating groups. They are electron withdrawing groups. They withdraw electron density from the ring, making it less reactive towards EAS. It will direct electrophile to metal position, making the ring electron poor, which destabilize the ortho and para intermediates. Common example of the activating group is nitro, cyano, and sulfonic acid.
As previously mentioned, there are two types of directing effect on the EAS reaction. So the first one we will talk about orthopara directors. So orthopara directors are substituents that can donate electrons by resonance. So as you can see here, when it's in the ortho and para position, they reveal multiple resonance contributors. But compared to the meta position, ortho and para will actually have a fourth resonance contributors in which the positive charge will be outside of the benzene rings and on the oxygen atoms here, for example. This will make the ortho and para position more favorable compared to the meta position due to its stable resonance contributor.
There are also substituents that can donate electrons by hyperconjugation. An example here is toluene. Toluene has an alkyl group as the substituent. When you add a nucleophile to toluene, to ortho and para directors, you can see there there is a partial positive charge that are created next to the alkyl group, which is electron donating. This makes the structure very stable compared to the meta position. The next one is meta directors. There are substituents that cannot donate electrons. For example, here is protonated aniline. In this example, the positive charge is sitting on the nitrogen substituent. When you attach a nucleophile to it, especially in ortho and para position, you can see that it creates a resonance structure in which a positive charge is sitting next to the positive nitrogen atoms. This makes the structure very, very unstable compared to when you put it in the meta position. So when you attach an electron withdrawing group to it, it will be favored to have a meta position.
So here are the list of orthopara and meta directors. As you can see here, the substituents that are electron donating are also activating the benzene rings because these substituents have a lone pair of electrons that can be donated to the benzene rings and activating them. The moderately activating group can also do that, but to a lesser extent than the strong activating group. And for alkyl, they have less electron donating effect compared to the previous ones, but they are still considered to be activating. And these activating groups are ortho-para directors. Now we go to the deactivating groups, which in this case we have a carbon that is attached to electronegative atoms, and these electronegative atoms will withdraw the electrons from the carbon and the benzene rings and deactivate them. For the strongly deactivating groups, we have positively charged substituents that will also withdraw electrons from the benzene ring to a greater extent compared to the moderately deactivating. And these are meta-directing as previously mentioned. But the activating groups are not always meta-directing. Here are the exceptions. Halogens are deactivating because they are highly electronegative and they withdraw electrons from the benzene, but they are ortho-para-directing. Why is this the case? Because when you look at the resonance contributors, ortho-para position will have the positive charge on a carbon attached to the substituents. And if that substituent is rich in electrons, it will stabilize the resonance contributor on the ortho-para position. There are many real-world applications of ES reaction. For example, in dyes and pigment production. The precursors such as nitrobenzene and aniline can be produced using ES reaction. Also, in drug synthesis in pharmaceutical, we use ES reaction because it enables us to modify the substituents of a compound. And for detergent formation, we can use sulfonation to create sulfonated aromatics that are key ingredients in detergent making. Also, Friedel-Crafts reaction that are used to create intermediates in polymer synthesis use ES reaction. And also in agrochemical compounds production, we can generate halogenated aromatics using ES reaction. And finally, we can also use it in fragrance and flavors production.
Electrophilic aromatic substitution makes up most of the reaction involving benzene. Substituents can have different effects on the reaction. The first one is activating group. They are electron donating and they will direct electrophiles to ortho and para position. The second effect is deactivating group. They are electron withdrawing group. They direct electrophile to meta position. But there are exceptions, which is the halogen substituent. They are electron withdrawing group but also ortho and para directing. EAS has various uses in real world, such as pigments, drugs, and fragrance synthesis. These are the reference used for our presentations. And thank you for listening.